Hi everybody, today we'll continue our discussion with chapter 4 on image sharpening. Okay, so what is image sharpening? So basically the objective is to enhance the detail. So if you know, detail info is typically containing the high spatial frequency components. So usually when we talk about image sharpening is some form of high pass filter. And high pass filtering, we can do it in both spatial domain and frequency domain. So in spatial domain, we do convolution. And in frequency domain, we use multiplication mask, like what we have discussed in chapter 2. Right? So we look at high frequency emphasis. So high frequency emphasis, actually, if you use only high pass filter, so the difference is from high frequency emphasis, high pass filter alone will only retain H, but you are going to lose all the original contrast, the overall contrast of image. So if we use high frequency emphasis, so we will retain some of the low frequency or the overall contrast. Okay, so actually you can perform that in spatial domain by using what we call high boost spatial filter mask, which looks something like this, where all the frequency, all the coefficients are -1 except the center are is positive. So in this case, if you look at this, the sum of all the negative is -8. So center, if you put 8, so which means the sum is 0. So basically you're going to get a high pass filter where you have only the H without the original contrast. So if you want to retain the original contrast, then you need to have a larger value. All right, something greater than 8, like 9, 10, the more the value, the more it will retain the original contrast. And if you use anything which is less than the total negative, like in this case, -8, so if you use anything less than 8, so you are going to get the negative of the original. And you can actually use a larger mask size to reduce the noise of effect, the effect of noise. So meaning that when you enhance, because H also appears to be different, so it will increase the noise as well. So you can use a bigger mask size to avoid enhancing the noise. So if you in this case, if you create an n by n mask, so how should be the center be? So the center will be something should be greater than the total negative value. In this case, 24. So if you use 24, then you will get a high pass filter. And if you increase more, then you get a high pass emphasis filter to retain the original image contrast. So I'm going to show you what I have prepared here. So first I'm going to use a 3x3 mask. I'm going to show you how it's going to enhance the noise as well. And I'm going to use a different center value, one which is less than the total negative, one is equal to the total negative, and one is greater than total negative. So as we expect, this will give you a negative. This one will be a high pass filter where you see H only. This one enhance H with some of the original contrast retained. All right, so you can see actually I'm doing convolution. So let's try to run it. So you can see in here. So here the center is 5, which is less than the total. Here I'm using 3x3 mask. So total is 8, -8. So if your center is less than that, so you get the negative of the original. So you can see original, the rise is brighter than the background, but here you see the rise is darker than the background. So it's actually the negative of the original, but you can still see the H is actually has been enhanced. So if you look at the mask here, the H here, so it's actually highlighted. You can see the H clearly. Okay. Well, if you use center 9, which is just 1 more than the negative, so you can see the original contrast is actually lost. So you see only you can see the whole image is grayish. You don't see much difference in terms of the brightness of the rise and the background. Like in the original image, you can see the rise is brighter than the background. But here, both rise and background appear the same gray. That means the original contrast is lost, but you can still see the H has been highlighted. So you have enhanced the H. So this one, the center pixel is 14, which is higher than the total negative, which is 8. And you can see that the original contrast is better retained. So we have the rise which is brighter than the background, but we still have the edge actually enhanced, highlighted as compared to the original image. Okay. So now I'm going to show you what happened if we actually increase the mask size to 9. You will see a thicker edge enhanced. So you can see the edge is thicker. Okay. And then, but you can see now the noise is not as much enhanced as compared to 3x3. See, the noise is very much enhanced. So I'm showing you the background. You see the background is not as noisy as compared to 3x3. All right. So that is basically about high high boost spatial filter mask. So next we're going to talk about homomorphic filtering. So this homomorphic filtering is actually developed based on this theory, where digital image is actually created from two primary components, the lighting and also the reflectance components. So the lighting components actually is the light that shine on the object and captured. So it will change according to the lighting. So the more light that you shine on the object, then the lighting condition will increase, and vice versa. And then there's the second component, which is the reflectant components. Is actually determine the object that reflect the light. So it's determined by the intrinsic properties of the object, which normally do not change. So in most of the image enhancement application, what we want to do is to enhance the reflectance components while reducing the contribution of lighting. So it's still the same concept of high pass emphasis. All right. So homomorphic filter is actually a frequency domain filter, different from the previous one. This is we do it in spatial domain by using convolution. This one we do it in spatial frequency domain, where you have to do the frequency transform. So in homomorphic filtering, so what we do is we try to compress the brightness component, the lighting, and we enhance the local contrast or the edges, details, which is actually the results from the reflectance properties. So according to the model of homomorphic filter, the image is actually a lighting component multiplied with reflectance components. Lighting is, the L is lighting, R is actually the reflectance. So in this homomorphic filtering, we assumes that the L, which is primarily the low spatial frequencies, which is responsible for the overall contrast, whereby the R is actually primarily the high spatial frequency, where actually is representing the edges, object boundaries, which is responsible for the local contrast. So based on that, it consists of 5 steps. The first one is natural lock. So natural lock actually serves to decouple this lighting and also the reflectance from multiply to sum. As we know, when we do lock, multiply will turn to sum. So this is actually to prepare to Fourier transform. So Fourier transform, when we transform, we're going to get frequency representation. So then you will see that these two will actually be separated. L component will mainly be in the low frequency and the R will be mainly in the high frequency. And then we are ready to do the high pass emphasis filter, where we actually amplify the high frequencies or the details of image. And then we try to suppress the low frequency component or the overall contrast. And then we try to do inverse Fourier transform, and also inverse natural log in order to reconstruct the image from the filtered spectrum. So usually we have 3 parameters in this filtering. We need to specify how much we want to amplify the high frequency, or this is called a high frequency gain, which is usually greater than 1. As we know, when we multiply with anything than 1, we're going to increase the value. And for low frequency gain is used to actually lower the magnitude of low frequency. And then also we need to set the cutoff frequency to differentiate between the frequency which is low and high. All right. So this is the results. If you do homomorphic filtering, you will find that usually the output is very dark because you lost the original contrast, the brightness, and you usually will have to do contrast enhancement after that. And you see if you compare the one that after homomorphic filter and also the one which you just merely do contrast enhancement of the original image, you can see in the homomorphic filtered image, the edges are highlighted very obviously. Okay, so I have also created the codes for this homomorphic filter, right? So let's run this. So this is my original image that I enhanced it, and this is the one after homomorphic. As you can see now, the edges are actually very much highlighted, better than this. And this is the high pass filter, where actually the low frequency in the middle, we multiply with something smaller, and this one we multiply with something bigger, the high frequency. In this case, we set the cutoff 16. Okay, anything 16 from the center is set to a high frequency, and we will multiply with 1.2, which is our high frequency gain, and this one multiply with 0.5, so that we retain some of the low frequency. As you can see, this image, the original contrast is less as compared here. The copter is much darker than the background, but here both background and copter appear to be more grayish. Okay, that's mainly because we have actually suppressed the low frequency, which is actually the original contrast, but we actually boost the high frequency, so that's why the edges appears to be more highlighted. But there is some problem where we have this, what we call the ripple effect. If you try to zoom in, you will find this ripple effect. You see all this ripple effect, which is not supposed to be in the original image. So this is because of the sharp change from low to high frequency. So we allow the change to be more gradual, like if let's say I change this to 20. Okay, so you will see that now my mask actually, after 16, I gradually change slowly to the upper frequency gain. So you can see that in this case, the ripple effect become less. Okay, but the highlighting is getting lesser as well. So basically, that is about homomorphic filtering. All right. So that is all for our. Oh, sorry. Still have another one, which is part 2 about unsharp masking. All right. So unsharp masking, basically, what we do is also we are trying to increase the high frequency and suppress low frequency, but we do it in a very unique way. So first we do low pass filter, that is we do convolution with blurring mask. So we blur image, and then the blurred image we try to reduce the contrast. So last time you wonder where we're going to use histogram string to reduce contrast. So this is where it is. After that, the one that has been blurred and reduced contrast, we subtract with the input image. And then the output, we try to histogram stretch to increase the contrast, and the final result is the sharpened image. And how much you actually shrink the contrast here will decide how much contrast you will actually reduce. So this is the sample where if you reduce, you shrink it from 0 to 100. So you get image like this, which is sharpened. And if you try to shrink less, so you get even more sharpened image, sharper image. But if you shrink even lesser, then you get image which actually lost the original contrast, where you see only the edges. So you can actually, this is actually trying to explain why when you adjust the string, It's actually, you actually adjust the X. Okay, so so if you look at here, what happened, the original spectrum, we have the low frequency more than high frequency. All right, so I'm trying to explain in terms of frequency components so that you can understand better why they do low pass filter. So when they do low pass filter, actually they're trying to remove the high frequency. So left only the low frequency, and then when you do histogram string, you're actually reducing the magnitude of low frequency. And then when you subtract, so basically you are trying to retain the high frequency while reducing or suppressing the low frequency. So this is practically a kind of high pass and persist filter. Okay, so you don't remove the low frequency altogether, but you actually suppress it, but retain some of it. So that is the effect that you get when you smooth and then you string and then you subtract. So you're practically trying to reduce the amount of low frequency while retaining the high frequency. And then when you do histogram stretch, you are actually trying to increase the high frequency. And of course, this one will increase, but because it has been reduced or suppressed earlier, so now actually the net effect is you actually increase high frequency more. And then you increase high frequency, and the results that you get is actually a sharpened image where the edge looks sharper. But of course, as you see, if you actually do not string so much, meaning that when you don't string so much, so this actually retain as its original shape. So you can figure out when you subtract, you are actually reducing the low frequency very much. So when you reduce too much of the low frequency, then that is what happened. You have image without the original contrast. All right, you can see that the whole image looks grayish as compared to the original, where the glory line is much darker compared to background. Okay, so this is what happened. So I've also prepared the code for Unsharp masking. I use 3x3, all right, and then I smooth it, and then I perform histogram string. So this is where I decide how much string I want. Okay, let's say I string more, 0.2. Okay, when I try to run, you look at the results, you will find that. So this is the image after you smoothen, and then you histogram string, and then you subtract from original. So you can see the image basically become darker because you have actually reduced the low frequency, which actually is the lighting or overall contrast. So you can see overall contrast less, but you can still see all the edges clearly because it's retained all the original edges, but it will suppress the original contrast, the brightness. And then as we go contrast stretch, we restore the contrast. We can see that now the image becomes sharper. Okay, what happened if we reduce less? As I said, when you reduce less, so you are going to, after subtract, you're going to throw away a lot of the low frequency or the original contrast. So you can see the image is even darker. So after contrast stretch, you can see the whole image now. You see only the edges clearly, and the original contrast now become less. So you can see the whole image become grayish as compared to the original. Okay, so you can have the bright and the dark very clearly, but this one, the background sky and the glorilla now appears to be very grayish. So now that shows that you have lost a lot of the original contrast or the low frequency. That's because you only string a little bit, and then when you subtract, okay, so basically you subtract out a lot of the original contrast. That's why you get a very poor contrast image. So even if you enhance, eventually you cannot restore too much from there, and then you get an image which has a lot of contrast reduced. All right. So basically that is about Unsharp masking and also about our lecture today. So thank you.